All right. And so today I realize we're kind of like off-centered. I would say this is supposed to be section 22, but we're really going to focus on the lots of 21, and then we'll go into A/B testing, which is what 22 really is, a little bit later. I may or may not see how things go. I might actually keep ANOVA to a slightly different date. And the reason why I really want to go into more detail about it. But if we do touch it today, I'll at least go over the parts of it and how it functions essentially, just to make it a little bit, like I kind of want to go through some extra like mathematics in it that the curriculum doesn't really talk about, which I think might help explain some of the things that like people usually ask questions about. For example, the classic is, how is ANOVA different from t-test? And just kind of spoiler is that they're really not different. It's just that essentially they're, ANOVA is more general in that sense, but it's really the same thing as a t-test or a statistical test. Okay, cool. All right, so I'll go ahead and share my screen. Let's see here. And there's my screen. Okay, so cool. All right, and you guys can all see that? Yeah. Yeah, you can see me wearing a sweater today because it was cooler this morning, which I like. All right, fall is finally here. Okay, so you don't need to look at old man yells at cloud. All right, so most of the stuff we're going to talk about is going to be still an experimental design. I kind of formed it around this way, so just kind of be able to navigate in here. But if you guys remember, we talked about our t-test, right, last time yesterday. And we talked about basically how you use this to essentially find your t-critical value, or sorry, your t-value, your t-statistic, right, using this formula right here for your sample, and then basically using your t-critical value, which is basically coming from your alpha value to determine, you know, your p-value from your t-statistic, okay? And note that basically you should think of like your t-statistic, your t-distribution, your t-critical value, those are all connected together to give you your p-value at the end. So I'm going to go into Welch's test. So one thing I had mentioned is that this is, I don't know if I actually, no, I did mention this. This is what we talked about is the student's t-test. So it's still a very powerful tool, but sometimes we can do a little bit better. So what the next part we're actually going to look at is our Welch's t-test. And so Welch's t-test is kind of like a modification of our student's t-test. And we'll talk about like what that difference is and why we would use those two. In reality, we probably will use Welch's t-test in practice more than a student's t-test, just because it's more robust, and we'll talk about what those differences are. But I kind of wanted to go over this visual, which is from the curriculum, but I kind of said it a few times, and in a couple one-on-ones I went over it, and I realized this is something that would be useful for as a whole cohort. So this right here, you can imagine, is our t-distribution. And what we're going to do, like when we do our, say, okay, we're going to perform a hypothesis test with a t-test, right? In this case, it's a one-tail. We get our t-statistic, we calculate this out. In reality, we probably would feed in our data, use some package to basically calculate the t-statistic, and it'll spit out the t-statistic, let's say 1.326. It'll also have an associated t-distribution. This is kind of what's going on behind the scenes more than like what you'll actually do. You could technically do it this way. I've seen people kind of shown it, but in reality, you probably don't want to like do the whole t-distribution value because you want to get relatively efficient. But this is what's going on. Essentially, we have our distribution here, and then we have our t-statistic, which is going to be from 0, right? And then it's going to go off to, let's say, 1.326. Okay, so this right here is saying, okay, this is our t-statistic. And what this part under here, we'll usually call this like area under the curve, or AUC. Okay, this is representing essentially like the extreme values of this. And so what we would do, we would compare this with our T critical. And remember, where did our T critical value come from? Like what thing is it related to? What letter of the English and Greek alphabet is it related to? I'll give you, it's a Greek letter. You only have two Greek letters, alpha and beta. So which of those, for T critical, would those two be related to?
Is it alpha?
Alpha, yeah. I know it's really nerve-wracking, like answering questions, right? But yes, it is alpha. And we also call alpha our critical value. So our T critical value is related to the critical value. Okay, I'm going to repeat those stuff because like I think it's important to see that connection. So essentially what we do is we define our critical or our T critical value from alpha, Okay, basically using the t-distribution. I'm not going to go into details like how you would do this, but essentially that's what you would do. And your t-critical value would sit along here. And essentially what's happening is that if your t-statistic, which is this guy right here, fits within, let's put your little trying here. Let's say we have like, this is our t-critical value. So this is our t-star, or t-critical, right? I won't write critical, but know that t-star and t-critical are the same thing. Essentially, this is saying, okay, like this is how much weirdness we're allowed to accept. And so if the t-statistic is outside of this area right here, then that means that we fail to reject the null hypothesis. Basically, it's like, oh, there's no real difference. But if this t-statistic, this t-value is actually within this t-star, t-critical value here, then we would say, oh, that is super weird. We need to reject our null hypothesis. So that's essentially what we're doing here. And what this area underneath here actually represents, does anyone got to guess what this area is going to represent? So many letters in statistics.
Is that the probability of a type 1 error?
Yeah, so alpha is kind of like saying what the probability of us making of type 1 error, but it actually represents in a lot of ways just our p-value. So yeah, it is the probability of making a type 1 error, which is our p-value. So essentially say, oh, if this value is very, very small, that means a small p-value, which means there's a small chance or a relatively small chance that we're making a mistake. We're making a type 1 error. So that's why essentially we're saying that alpha value is like, this is how much of a mistake we're allowing ourselves to make. And it's like, okay, like it's very unlikely for us to make this mistake. So this p-value might, for example, represent something like, oh, this is 0.08 or something like that, okay? And that would be the area. What's the area under this curve? If we were to fill out this whole curve underneath, what would be that value? It's a number. It's one of the best numbers. Yeah, 1. Good. So like I said, like if I ever ask you a question, it's pretty much either 0 or 1, right? So yeah, the whole area underneath this curve should be 1. So that's why our probability here is 0.08. Basically, that's what's being represented from. Okay. So kind of scrolling a little bit further underneath, the curriculum kind of mentions that is that if you were to use a CDF, remember our CDF, and say, oh, that's kind of funky looking, we can actually get the PDF directly from here. So if you imagine on this x-axis is your t statistic, and we made a CDF instead of our PDF, which is like up here, right? If we made a CDF of the same distribution, you would see right here would be your p-value. So you would actually pull out your p-value from here. Now note that I should say it's not really your p-value because it's doing everything to the left of the distribution. So really it should be 1 minus this would give you your p-value, but this is going to represent your p-value right here. So 1 minus this would give you your p-value. So you can kind of see this similarity is that if we had our PDF, which would be in this case the t-distribution, and on the bottom on the x-axis here is your t-statistic, this would give you your p-value, whether it's like just the value on the y-axis on the CDF or the area underneath the curve over here. And again, I should say again, it's not really your p-value, it's 1 minus this is your p-value. Does that make sense to everyone? Okay, I see kind of head shake, kind of. Any questions you guys want to clarify or?
So sorry, you're saying that the point, like 0.7 is the p-value for the CDF, which is also equal to the area under the curve.
Yeah, I guess I should be careful about this. If I'm talking about something that's less than, so if I'm looking at like a one-tail test, it would actually be this part of the area. So it'd technically be 1 minus this value right here. So the curriculum puts a P, it really should be like, I don't know what to call this exactly. I want to put like Q or something. So like it's 1 minus this because we want this part right here.
Sorry, so 1 minus, so Q is equal to 0.7 or P is 0.7?
Yeah, so this would be like Q, I'm making up just a number or a letter, Q, and then so our P value is equal to 1 minus Q.
So the p-value is 0.3, which is what we saw earlier.
That's right.
And so is 0.7 also the green area to the left? there?
That's right.
Okay, so
Yeah.
that's actually Q2.
Mhm.
Okay, thanks.
Cool, no problem. Yeah, so just know that this is kind of like how you would find the p-value directly from the t-statistic or from the t-distribution. So this would represent your t-statistic or your t-distribution. This would be your t-statistic, which would give you essentially the area underneath the curve, which can then give you your p-value. So that's how we kind of translate it. There's other ways you can do this too. You can actually, just like we did like I kind of mentioned, is that you can take your alpha value, which is 0.05 usually, and transform that into a t critical value. That's where that chart is. If you ever look like on statistics and stuff like that, you can transform your alpha value. It's like, oh, I want an alpha value of 0.05. And then it says, oh, what's your degrees of freedom? Basically how many samples it is. And then it tells you, oh, this is your t star or your t critical value. You can go the opposite way, where instead of saying, okay, let's find alpha to get our t critical value, which will give us p value, we can instead say, okay, what is the area underneath? Sorry, I'm just put this here. Like, what is the t statistic transformed to a normal distribution? And that will basically put this here, and then you can get the p-value directly. Note that you just might see it either way. It's the same thing. It's whether you transform your alpha value to a t critical, or you transform your t statistic into essentially a z statistic. So either kind of one works either way. It's just kind of like which direction do you transform it to. In reality, you don't really need to know like to think about this every single time when you do a t-test, but this hopefully gives you an idea of like saying, oh, this is why we're able to do this. This is what the p-value is representing. And what's nice is that once you understand that there's this distribution here, and you basically have your t value, your z value, whatever your z-score, whatever this thing is right here, your t statistic, okay, you just replace whatever you're testing with a different one. So if we talk about like an F test, well, an F test will have an F distribution. It will have an F statistic, which will give you a p-value. And essentially you just replace whatever letter here with, like F essentially. And then you can just say it's the same exact process. Okay, cool. Any questions on that? Does that sound decent enough? I think I kind of keep harping on this just because like I feel like it'll be useful when you say, people usually go like, there's so many different tests you can take doing statistics, like what's going on? And just know hypothesis test does the same exact process every single time. It's just a different distribution. Okay, cool. All right, so kind of review a little bit of like, of t statistics and like hypothesis testing. Now we can say, okay, Welch's t-test. So Welch's t-test is going to be pretty much like the student's t-test like we just saw, except we're just going to calculate the t statistic differently, and it's going to be a slightly different t distribution. Okay, so there's a little Wikipedia article here. Just know that our students' t-tests, I think we mentioned this before, but to be explicit, is that we're assuming the sample sizes between the two, getting like, for example, if two sample tests, these sample sizes are the same and the variation of the samples are the same. So note that this isn't always true. For example, if you're collecting between like, if you have 32, men and like 42 women, and you want to test between the two parts, they're probably not going to be exactly the same sample size, and also their variation will change. And so this will kind of be most obvious if we actually look at like the formula itself. So Welch's test basically modifies the way we calculate the t distribution or the t statistic and the degrees of freedom. So the degrees of freedom, we'll see like how that kind of changes. It's a little more complicated, but the first part is looking at the t statistics. So if you remember from our t test, and I'm going to go back here real quick, this is how we found our t value, right? And we see x, basically a mean minus another mean divided by the standard deviation. Well, the problem is that if the standard deviation, the sample standard deviation is not the same between these two different groups, this formula wouldn't work out well. So what Welch's test basically does, like, okay, let's consider the standard deviation of that one sample, standard deviation of the second sample, and then adding those together divided by each of their, basically the number of samples, and then taking the square root between those two. Note that if we were to say that S1 equals S2 and N1 equals N2, that would just simply give us, let me draw it out right here. If these were equal to each other, that would give us the square root of 2, I see here, is that right? Oh, sorry. Yeah, no. I mean, that's right, yeah. S squared divided by 2, or sorry, N. Which essentially will give us S divided by the square root of n. Note that we also get like a square root of 2 here, but that's less of an issue. That's like a normalization factor. So we could really kind of like ignore this part. But the point is that this essentially simplifies to our student's t-tests. So this is actually what we would use for Welch's t-tests. This is what you normally would use in industry, is that you probably would do a Welch's t-test over a student's t-test because it has less assumptions, being that the variance in the sample size are different. Okay.
What does SE stand for?
It's just kind of, I'm trying to remember the exact phrase of it. It's essentially the normalized, not normalized, standard error, if that's right. So it's incorporating that standard deviation with the number of samples. So it goes beyond like our standard deviation, because if you have a standard deviation of 10, but you only had like 10 participants, and then you have a standard deviation of 10, but then with like 5,000 participants, that you're going to be more confident in the sense like, oh, well, if you had a smaller number of people, there's a chance you picked things from the very like extreme sides. And so maybe your standard deviation shouldn't be that large. So essentially that n factor is correcting for the fact that it's like, oh, if you have many, participants, your standard deviation is relatively like certain. Okay, cool. Anyway, so yeah, there's just a way to represent this SE is this guy right here. Okay, cool. All right, let me clear this up then. Cool. So the next part, which I'll be honest, there's a little confusing. Don't worry too much about it. This is our standard, our degrees of freedom. So notice like a lowercase v right here, that our degrees of freedom is actually changed to. So before, if you remember degrees of freedom for t statistic, it's just basically the number of samples minus 1. Degrees of freedom will slightly change because the number of samples is not consistent, right? So between the two. So basically it averages it through here. And let's see here. I'm trying to see if I have any little extra notes. Yeah, no, so basically this would get you your degrees of freedom, and then you would say, okay, from this degrees of freedom, you would find the t critical value for Welch's tests. So essentially that's what you're using the degrees of freedom to basically modify what is your actual critical value that you're going to compare it with. And essentially this represents the fact that the Welch's t distribution is slightly modified. So that's essentially what we're considering. Okay, cool. In reality, do you have to write this down or memorize this or ever call this from memory or even look it up? Probably not. Like in reality, you're probably never going to look this up yourself. You probably will use Welch's test, or you code this once and then you save this in your nice little file, and then you have a function that's all set and ready to do a Welch's t-test. Okay, cool. Awesome. Any questions on how these modifications apply to Welch's t-tests, at least different from our students' t-tests? Okay. Thumbs up if we're feeling good. I haven't scared you guys too bad with like these weird looking equations. Okay, cool. So nice thing is like, okay, let's just see how you'd do this in practice. So, all right. So I wanted to show you guys really quickly from again, I'm using SciPy. I think the curriculum might use something different, but I'm going to intend to use SciPy. Is that here's the documentation. Note, basically, we're just going to put in A and B, which is going to be our actual samples. So note that I don't have to calculate anything special. I'm just like, oh, just put in the samples A and B. It will figure out how big those samples are. And then it will say, okay, equal variance. So if you say equal variance is equal to true, this is going to imply saying, oh, it's going to use a student's t-test. Basically, it's going to assume that these sample sizes or sample standard deviations or sample variances are equal to each other. If you say false, this will actually default to a Welch's t-test. So note that this, even though this is a t-test index, there is no Welch's test in SciPy. This is how you would get a Welch's test. And you can see here, if false, perform Welch's t-test, which does not assume equal population variance. Okay. And then there's some extra parts in here, which you don't usually have to worry about. So let's check this out. So I made a little function here to make it a little bit easier for us to compare the two. So I'm actually going to perform a student t-test and a Welch's t-test. So you can see here we have students t-test is just basically our samples A and B. Okay, and then our Welch's t-test is the same thing, except this time we say equal variances equals false. And this is tells SciPy, okay, don't use a student's t-test, use a Welch's t-test. Okay, And then note right here, I'm just basically printing out some interesting stuff. So I'm going to compare students, our students, oh, sorry, I should mention that students in Welsh's, this students test index, as we saw from this part, will return the statistic, so the t statistic, and then the p-value. So this will actually return a tuple like this. Okay, so if you just ran this by itself and you got these numbers, you're like, what the heck is this? Like, why are there two different numbers on here? You have to go look in the documentation and double check, oh, it's coming from the fact that the first one is the statistic, the t statistic, and the second one is the p-value. Okay, cool. So, and then you can just see, we just compare the t statistic and the p-value. So just to kind of see what the difference is. So, oh good, I already ran this before, but we'll run this again. So I'm just going to create here just some random states, 27, just so I have consistent results each time. And I just chose these parts relatively random. I try to make it so it's a little bit different, but note that these are the same means, right? So this should show like that they aren't any different from each other, right? That in reality, these samples should really be the same, you know, from the same population, but I have a different standard deviation. So I'm pulling this, note, remember I'm getting random data. So I'm using a standard deviation 50. So that way you have, you know, different variance, and then we have a size of 10 versus our other sample, which is going to be from the same mean, but a different scale and a different size. So when I run this, which I think is right here below, we can actually see our C statistic. So we can see the T stat from students is 1.82. We can see Welsh is 1.78, so a little bit smaller. And you can see the difference is about 0.039, right? So you can see like, okay, there is a difference between the two. And then you can see our p-value, right? So our p-value is kind of interesting here, is that they're both not significant, but you can see they're pretty close, right? So like if, for example, let's just say we had an alpha value of like 0.08, students' t-test would actually say, oh, there is a significant difference, where the Welsh's t-test would say, oh, no, there's not a significant difference between the two. So note that basically it's a little more robust in that way. Now, since the student t-test in general is relatively robust, but this also capes for the fact that different sample sizes and different variations. We could maybe modify this a little bit more, right? I was trying to get it to, I think, to the point where I had like something where it's under 0.05 and it's slightly above 0.05, but that was mostly me like fiddling around. So you can see here, as I increase the size here, you can say, oh, it's more likely for it not to mess up. So let's try if I can do this real quick. There we go. Here we got a significant result for student t-tests, 0.03. We can see here for Welsh t-test, we think it's not significant. And that's because it's taking into account that the scale and size are not the same. Okay, so you can see how this can actually have an effect on like how you proceed in like your in your test. Note that if I have the same values here, let's do 25, they shouldn't have any difference between the two, because essentially that size and scale, even though I'm doing a t-test, a Welsh test here, or sorry, a Welsh test right here, and a t-test right, or student's t-test right here, there's no difference between the two. Note if I had like slightly different, right? It's a little bit different, right? So you can see there's a slight difference on here, but for the most part, it's relatively the same. Okay. Any questions on you guys have that? No? Cool. So my suggestion is using Welsh's tests because it's more robust, and worse is that like there's not like a real reason, like I would say back in the day, like you would say, oh, Welsh's t-test is more complicated because you would have to calculate your degrees of freedom, your t-statistic, and you have to consider all these parts. But in modern day computers, like you can see this, taking a student's t-test and a Welsh's t-test literally just has an equal variance equals false is like the biggest difference between the two. So like this is like nothing. And if you're wondering about compute time, it's about the same. So even if you have very, very large data sets and you were doing these statistical tests, you probably would be fine either way. Cool. All right, so that is our Welsh's t-test. Okay, so use Welsh's. Cool. All right, so let's move on to our next part, which is statistical power. So I think statistical power actually comes from section 21, what we were supposed to go over last time, but we hadn't actually skipped over statistical power to get to Welsh's t-test, but I think that more was relevant to what we're doing. So for statistical power, note that this basically relates to our false negative rate. So just run this a little bit. So one we can think of like power, and note this is just, there's not like a real reason why we couldn't just simply say beta, but just from, I don't know, history, I guess, you have power is defined as 1 minus beta. So if your beta is 0.2, remember that's 20% false, we're allowing a 20% false negative rate, power would be 0.8. Okay. So it's just a way of defining things, but there's not like a real reason why we have to do that. Okay. So just kind of quick things about numbers. Just always useful to kind of think of this in your head is it's power goes from 0 to 1. If you have a power of 1, basically it means you have no false negatives, right? Or the likelihood of you getting false negatives is essentially 0. 1 is if you had a power of 0, right? Well, that would mean basically you have many, like all of the parts you can get are false negative. Like there's a pretty high chance of you getting a false negative, which if you think of it this way from the two different distributions, let me see if I can draw this out real quick. Yeah. So if I had like a distribution that looks like this, and I'm using the same color because I'm too lazy to change over, and a distribution like this. Okay, so this is distribution A, this is distribution B. Okay, what's the likelihood of me accidentally saying B is A? 0, right? Yeah, so like basically beta is 0. There's no way I can get a false negative essentially. There's no way I'm gonna accidentally claim B when it actually is A, right? So our stat power, so I'm just gonna power equals 1. Okay, so basically it's like, oh, you have strong power. That's kind of like why they do this 1 minus beta. If I, however, had something that looks like this, and I'll use a different color for this one. Pink, why not pink? Or magenta. Oops, that's not what I meant to do. Okay, so then if I had something that was closer to like this, and I'm not gonna be a perfect drawer, so like this, and this is B, now we can see our power is relatively low. Like it's gonna be really, you're gonna make a lot of mistakes when you're gonna say it's B and A and we're gonna mix up the two. So our false negative is going to be closer to like 1, right? And our power will be close to 0, okay? And essentially means like there's no way for us to really know like between the two based on these distributions. So just kind of know that set difference between the two. And I like to keep these things in mind. If you had something a little more reasonable, like something that looks like this, right? Your power would be something like, oh, like some value. And usually we aim for a power of 0.8. We consider that as like a good statistical test. Note that one factor is like the actual effect size, right? So if I change the effect size from here to here, right, that will change our power, right? So if I move these distributions closer and closer, our power would decrease, right? So a smaller effect size means a smaller power. Another subtlety in this part, this I don't think is super clear, is that these distributions themselves, right? So if I had like a distribution that looked a little different, so this is a normal distribution versus a t distribution versus some other distribution, this will also affect the power. So actually what kind of test you're doing, whether it's a t-test or let's say like a z-test, for example, those will have different powers. So that's something to keep in mind and we'll come talk about it a little bit too, just very briefly. So, all right. So this brings me to this little example, which I love this visual right here from this website. So this shows a great way how they're all connected together. So typically, let's try, for example, our power. So since we're talking about power, let's say significance level of alpha, right? And all we really care about is our beta. So now that if I change my alpha here, it's saying how much we're allowed to essentially allowing ourselves to say, oh, how weird something is. So that will actually change how much of this beta that we're crossing over. I'm going to do a one tail as well, so that way it's a little bit easier. So you can see here, if I have a very low alpha, basically those rest of these parts are going to be false negatives versus these are going to be my false positive rates. Okay. If I increase the sample size, what would we expect if we increase the sample size? What will happen to these two different distributions? Well, how will they change in shape? Or how would you expect them to change in shape? So I want you to think about that for a second and then let's adjust it, right? So you see how we actually got steeper ones. And why would we get steeper ones? Has anyone got a good reason for this?
Because there's more data to like have it be like a less, wait, no,
Mm-hmm.
I lost it.
I think you were, I could hear like the gears turning. I think the big thing, the sample size, is if we have many samples, it means that we're more confident in the sense of like, we're not pulling it from the extreme parts. But if we have very few ones, we're not really sure where we pulled those individuals from. So essentially it's like modifying the standard deviation. So essentially by having a large number of points, we can make our standard deviation smaller, or effective standard deviation smaller. And if we had very few points, it means like we're really not certain if we pull, you know, our sample from the extreme ends of the population. So our sample standard deviation is going to be larger. We're going to pull more variation. Okay, cool. So then our last part here, let me just reset the zoom so it's a little bit easier for us to see. And the effect size. So the effect size is going to adjust it smaller, make it either closer together or further apart. So if I make it smaller, we're going to have more beta right here, right? We're going to have a lot more difference. And you can see here is that our power, where's the power? 13%. So you can see 13% is relatively small, versus if I change the D over here, you can see power is 100% because there's no crossover where we'll accidentally claim a false negative, right? We won't reject the null hypothesis, or fail to reject the null hypothesis when we really shouldn't have. Okay.
Sorry, Victor, do you mind going over the significance level one again?
Yeah, this guy right here?
Yeah.
Yeah, so note that basically our alpha right here, like so say it's 0.1, right? That means basically this is our, what's it called? Our type 1 error, right? So we make a false positive. So we reject the null hypothesis when in reality we shouldn't have. So you can kind of imagine, I don't know how to go after this. In this case, you can look at like for our critical value, or we're looking at a z-test. This is our critical statistic. And so our critical statistics, like everything to the right of this, we should reject the null hypothesis. But if we were over here, it's like, well, maybe we really shouldn't have rejected it because there's a chance that we actually made we made a mistake. We just happened to pull very extreme values from this distribution. Okay. Yeah, hopefully that kind of makes sense. Does that help, Lauren?
Kinda.
That's much. Do you have a specific question about like their alpha or significance level?
Yeah, so is there something like as alpha increases, then there's more chance of a type 1 error? So then there's like, is it a bigger like overflow into HA, right?
Yeah, I think I hear a little bit what you're saying. Yeah, if we adjust our significance level, like essentially you can think of our significance level as like how much weirdness would we be allowed to do? Like what's our acceptance of like making a mistake, of making a false positive? So by nature, if we make smaller claims, like okay, we want to be really, really certain before we claim that the null hypothesis, we can reject it. We're going to have very few times we're going to accidentally reject the null hypothesis when we really shouldn't have. But this will affect directly our beta in a way, because our beta is going to say, okay, well, if you're not going to reject it, but you should have rejected it, then you're going to make that mistake too. So maybe you should have rejected it in this part. And that's where you can see if I adjust the significance level, you can see our beta are in this dark blue here actually changing.
Yeah, okay, that's helpful.
Yeah.
Thank you.
Okay, no problem. Cool. Good question though. And there's no, for two-tailed test, it's the same thing, but you just have one on either side. Note that you can never basically get this part unless you like, I guess, swapped over. But you can see here is that we won't actually make this mistake of rejecting it since there's not that crossover. Okay, cool. And note that this basically is all dependent on each other. We can change these things, but these are all interconnected. So you can see here, I can actually adjust the power, right? And this will actually figure out what our sample size needed to get this power with this significance level with this effect size. Okay. Cool. All right. So I think it's a great one to kind of play around with. So I really recommend just like playing around with this website and just kind of get a feel for like how these things change. So then it comes to say, all right, why do we even care about statistical power? Excuse me. So let's see here, adding more samples when P is close can lead to statistical significance, reject null hypothesis when we really shouldn't. So essentially what we're saying is like, how much are we willing to like reject or not reject, you know, depending on this part. So one thing to note is that we can add sometimes, like this is a classic where people, this is kind of like p hacking, but a little more subtle, is that if your p-value is relatively close, like, oh, it's really close to being significant, should I just add more values in there? And maybe, for example, that'll show like, oh, I really shouldn't reject it, or I shouldn't reject it. The problem is, like I mentioned before, is that you're going to be biased in that way of saying, oh, you're only going to test this if you don't have a significant value. You're never going to keep testing it when you already have a significant value. So what happens is that we can actually use a power calculation beforehand, before we actually do the experiment. So instead of saying, oh, we have 100 people, but our p-value wasn't quite right, do we get more people? Well, what you could do instead is say, okay, before we even collect this data, say how many people should we have to get this statistical power. So this is what we call like a power calculation. And essentially it should be done beforehand. So this will be important when we move into A/B testing. Essentially this is what A/B testing really is. But essentially what you say, okay, we're going to say we need a power of this level, usually 0.8, and we want a alpha level of this, usually 0.05. And then usually say, what is the expected effect size? And say, okay, what's the expected effect size, or what's the effect size that would make it worth it for us to actually make a change? So for example, if you're looking at like, let's say clicks per like your click-through rate, right? So how many times you click every time it's viewed for like an ad, maybe you're only worth adjusting the ad if there's a click-through rate of increase of like 0.7, like let's say 17% or something like that. Say, okay, like that's our effect size. That's what the effect size we want to see. So what if we want this effect size with this power, with this alpha, how many participants we would get? And that would give us the number of, basically the number of sample, or your sample size. Okay. So does that make sense to people? How these would all connect together and you could use this to find your N? Okay, so some quick scenarios, right? So these are kind of like different ways you can use power. So one is basically your effect scenario. So one thing you can think of is like if you have a large effect, right? A small number of points will likely give us p-values to correctly reject, right? But if we have a small effect, so if you imagine your distributions are very, very close together, you're more likely to get more false negatives, right? Where you're basically crossing this over. So just kind of looking at this right here, if we have a normal or a small effect here, you can see is that we have something that's relatively easy for us to make a mistake versus a large effect. You can see that there's almost like you're very, very unlikely to make a mistake between this part. So your power's higher here versus over here. Okay. Variation. So one thing to kind of note is that if your variation is small, right? So a variation, when I say variation, I'm talking about standard deviation, right? Or your variance, right? So if your effect is small, your variation is small, then you have a higher probability of getting the correct thing, right? So it means that you're unlikely to make a mistake, so you have a higher power. But if your variation is very large, you have a very like flat out distribution, well, it's just crossing over more of that area. So you're gonna have a like more higher or a lower probability of getting it correct, or a lower power. Okay, cool. And then same thing with sample size. So this is kind of like repeating the same stuff, just reiterating, is sample size is small. Sometimes we're likely to get extreme parts, so our confidence is smaller. So we might, for example, when we're pulling the sample from the population, get extreme values from that population, which is going to make it look like we should reject the null hypothesis when we really shouldn't, or vice versa, right? So the effect size is large. It means very likely, oh, I didn't finish that word. We'll just get rid of this because it's opposite. So effect size is small, but sample size is small. We need a large sample to be confident. Yeah. So if the effect size is relatively small, we need a lot of participants, right, to make sure that we're for sure not making that overlap. So eventually we're making that distribution skinnier, like we saw in that adjustment. Okay. And let's get a quick note is that statistical test itself can affect, like I mentioned, the distribution itself, but a t-test, student t-tests, and Welch's t-tests are relatively robust, so we don't have to worry too much about that. Note that in the power calculation, if you use a package to calculate this, it'll figure it out for you. You don't have to worry about factoring in the fact that you're using a t-test, because you're using essentially a t-test to calculate the power anyway. So, but note that t-tests are pretty good, so you don't have to worry too much in the sense of like, oh no, like, is this distribution good or not? Okay. Cool. All right, so this is just reiterating the stuff I kind of showed visually, but any questions you guys have on this connection? Okay, cool. Right. So actually performing this calculation, right, is how would you do this? So there's a couple ways you can have this done. So this is kind of going away from A/B testing, but it can be related. But here's the main thing. So one thing we can do is we use old data, public data, or we guess that your experiment is similar to another. So it's some experiment, some known knowledge, right? Say, okay, this is what we expect the actual effect size in the population to look like, okay? So then we use that to determine the effect size, check out the means and standard deviations to get an idea of the distribution. So we can basically look at our previous data, because in reality, we probably don't know the full public data, or not public, population data. So we can use other information, say, okay, well, we have this effect size from another experiment, or we can guess that the effect size is this much. Maybe there's some like suggestion of like, what we'd expect or something like that. And we can get an idea of this so we can determine our effect size. And then from there, let's see, our variation of the mean sample from sample means is standard error, so SE, right? Standard deviation. So just note that this is something that we can get. It's like, okay, we can actually get the standard error from it. Similar, like just looking at this other experiment, and then we can use a computer to solve for n. Okay, so essentially we can use this to determine effect size. We can use the standard error to figure out what n we need, and then we have the computer to solve for n. Okay, so if we have data itself, if we already have this stuff, we can calculate the effect size from that data and the variation, and then use the power that we want. So remember, we say we want this power, usually 0.8, to determine sample size. If we don't have data, you essentially want to assume, there's a couple ways you can do this. One is that you can assume a sample size and then say, what's the desired effect size? So it's like, okay, like, let's say we have this sample size, we say what effect size we actually want, and this will give you how much variation you need for a good power. And then you look at the variations, like, does that seem realistic? Does that not seem realistic? And if it's too small, you just increase the power, or sorry, increase the sample size. Or you can say, well, we're looking for a larger, let's see here, a larger effect size in order for us to do this part. So this is something you can do, like, you can kind of like iterate over this part to kind of get an idea of like what kind of power you really need or something like that. But this is kind of leading into what we would get for our A/B testing. Okay, cool. And I kind of linked down the one from the curriculum. I think your link is going to be slightly different, but doing online statistical power. But these are going to kind of use. They're more like, to be honest, I feel like a lot of times they're more like word problems of like saying, how would you actually like find this statistical power? That's more or less what you're doing. Okay, cool. So cool if I move on to A/B testing then. Sound good?
Maybe another name for variation.
Standard deviation.
Okay.
Is that, yeah, if that kind of spread, I'm trying to think of other ways you can phrase it.
I just don't remember the lesson saying variation, but then in one of the labs it had a VS, so I'm guessing it's that. So I don't know if I just was mistaking it for something else. But.
It might be. I'm not familiar with the lesson itself, so I could be wrong. The V sometimes can represent degrees of freedom, so it's all context. But when I say variation, you should really think of like, oh, standard deviation or the spread of the data. I'm just using this more as like a general term. If that makes sense. It's not like we can talk about the variance, right, which is basically related to our standard deviation, and that's really what I'm talking about. Okay. Cool. All right, so I'll move on to A/B testing, and then we'll talk about some warnings. So quick thing about A/B tests, basically, it's hypothesis testing, but it sounds a lot cooler, I think. Like when people say, oh, do you know A/B tests? They're just talking about, can you do hypothesis testing? That's essentially all it is. The classic example that people use a lot is like saying, we have a new layout for a website, or we have a new ad structure, and we want to see how many people either like click on this ad, or how many people, actually buy a book from this website given this layout and stuff like that. So essentially what you are doing is like, oh, if we make this effect, will this actually affect how the people who are interacting with this thing change their behavior? Okay. Note that technically this is kind of correlation. So there might be some factors in there and stuff like that, but that's the whole idea of what we're doing. So there's some kind of quick caveats. It's like, when shouldn't you use this? Or at least be careful when you tread lightly, because honestly, he probably wouldn't say, oh, I'm not going to use this. You're probably like, okay, we're going to do this analysis, but we'll be careful about the results. So basically, one thing is like when you give new features to old users, there is a bunch of things that you can go like have other effects beyond this. So one is the novelty effect. Has anyone heard of the novelty effect before? Okay, so essentially it's that the newest thing is like cool, right? You're like, ooh, like the new iPhone came out, or the new whatever came out, and you're like, oh my gosh, that's so awesome, right? And there's like everyone wants to try it and everything like that. So I kind of get this little scenario. It's not the perfect analogy, but it's close. Like a town's been out of soap for 3 weeks. New shipment comes in, and it's like, wow, we sold out all our shampoo on our first day. Everybody really like this. So like now we could really stock up on soap or shampoo, and people will buy a whole lot of it. Well, probably not, right? It's because it's a new thing that kind of changed. And you can think of it too as being like the cool factor, essentially. It's like, oh, like this is a new thing. Like I don't know about you guys, but like when I like have an update for a phone, I'm like, oh, cool. Like, and I start exploring all the features and stuff like that. And I implement the new thing and like, oh, cool. Let me try this out. That's the kind of effect that you want to be careful with. Kind of similar, but honestly, the opposite of this is change of version. So it's kind of like the equivalent of having someone who's like, oh, they're stuck in their ways. They want to do the same thing, they hate that it's this new change, the classic, like for, I guess like phones, I just keep going through because they've been kind of changing recently. It's like, oh, they got rid of like, if you have an iPhone, they got rid of the home button, or like, if you're using Android, like, oh, they changed the way the structure of like how you navigate the phone. And people are like, oh, this thing sucks. This thing's awful. Like won't use it, or people just won't use as much, stuff like that. So I kind of like have this little graphic. I remember like old people yelling at clouds. I'm pretty sure that's what people do. How can you avoid this? Any ideas? Because these are real effects that can happen, right? So how do you avoid this when you're doing your A/B testing? So you introduce something new, and you have to consider the novelty effect and change of version. Any ideas?
You could present it to an entirely new audience. I mean, that's one way, so that they don't have an opinion about it. And you're basically saying, if you were to have this thing, would you want the red version or the blue version?
Mm-hmm. Yeah, that's good, right? So like, especially if you are a relatively small, like, organization, and you want to expand this out to, more users of that, it might make more sense to really consider those newer users, right? So you can specifically target, say, okay, we're not going to give this new version or this change or this A/B test for old users. We'll only look at new users, right? Note you might still have a little bit of novelty effect in the sense that they're the first time using it, but at least you get an idea, right? Similar to this then is, and it's kind of like the same idea, is you just wait. You just wait for basically new users to come on, and that's essentially what you're doing. Or you wait for like I say, like the old users to die to replace new users. Essentially just means that you have more new users than old users to wait. So for example, if you're like your business saying, hey, like we don't got time for, new users to come in kind of deal, you can start implementing it now. Be aware that, these are older users, and then maybe give it time for older users to get used to. And then as you're waiting for those older users to get used to it, you can possibly have new users come in to do this test as well. So usually A/B testing is done over a length of time. Now, exactly what amount of time, it all depends, right? This is something like you have to decide, for whatever thing you're doing. For most websites, that might just be like, that could be like a month. It could be longer. It could be shorter. It just all depends on like what you're seeing. Okay. Any questions on like these effects and how you prevent them? Sound pretty good? Okay. Cool. So let's see here. I actually don't remember what I wrote under scenario. So let's see what scenario has to say. Scenario. Okay. All right. So, oh, that's why, because I didn't finish this. This is something for the future. I'm just trying to develop. So I'll just put this out here a little bit of like what you would do. I don't have the actual code that would work on this here. Is imagine that we have like a website, for example, when you want to see, how many times, the user actually like goes through like the next process. And maybe you can do things like you can change like the format or change, like the color or something like that. And you might have something like a click-through rate, basically saying the number of unique clicks at least once per unique views. So this is CTR is pretty typical if you're talking about anything with marketing or anything with computers and stuff like this. And just know that basically it's the number of unique clicks divided by the number of unique views. So this is one way we can use a metric, right? To say, okay, we use this metric to go through. Note that we'll talk about this a little bit in warnings, but this metric might not always be the best idea. You might have to do other metrics and have to consider like what makes the most sense for your data, and also think about like what your metric is actually measuring. If that makes sense, is that if you start seeing a certain thing and you neglected some action or behavior of your participants, you might think of based on your metric, like, oh, cool, things are looking really good. But in reality, you're basically biasing towards a certain direction because only a certain group of people were doing a certain thing. So just kind of be aware of that stuff. But what you could do essentially is you could boot sample the sample. Just try to read this a little bit. Try boot sampling the sample to account for, oh, I didn't finish this sentence. See, this is all work in progress. But you can basically boot sample to bootstrapping. So basically that means like collecting, you take a sample and you basically randomly select from that sample and you simulate, essentially say, okay, this is my new sample from that sample with replacement. So you would get some copies and stuff like that. But the idea is hopefully your sample would be more representative of the population, and then simulate the data to create a distribution of metrics. So you can basically say, okay, like, well, if I bootstrapped from this sample that I have and say, what would they likely do? And then you can do this over and over and over again. And it's kind of similar to building the set from the central limit theorem, essentially getting a sample, a mean of samples. So essentially that can help you get a little more scenario beyond just like your small group. And hopefully that can also give you some stuff. This is a little more advanced stuff. I was going to show it to you guys in here, but honestly, wasn't able to finish this part. It's still a work in progress, but something we can kind of consider for next time. Maybe I'll have this ready for like Friday Feels or something like that. I can show you guys what I'm talking about. I'll say we're that for now. So multiple comparisons. This is kind of like an issue here. So this is kind of related to A/B testing, but it should be also kind of considered when we're just doing any hypothesis testing. So the main thing here, I linked over to multiple comparisons problem, is that if we make many comparisons, so we look at like many different aspects of a participant or like of a sample and say, okay, like, well, what other things they have and different metrics they have. One issue you might have in here is that we're more likely to catch false positives, right? So if you basically just keep looking at different metrics, eventually you might say, oh, wow, there was an effect in this way, but maybe by chance it just happened to be just randomly say, oh, it looks like an effect, but in reality, it's just by random chance you saw some change in here. So there's a few ways we can do this. This directly relates to like our t-tests. So if you did multiple t-tests over and over and over again with different metrics, you might see an effect in one of those metrics when in reality that effect doesn't really exist. Think back to when we did the XKCD comic with the green jelly beans. Where they basically tested each jelly bean and eventually they saw an effect. That's what multiple comparison is. So I will put a little caveat is that I was talking to a couple of people about this, and the Bonafide, I can't say this right, Bonafironi correction and the Holm-Berfoni method, both of these things, to be honest, are not done too much in practice other than academia. They tend, mostly because it takes more time and they're relatively conservative, that it's kind of one of those things where businesses tend not to want to like take the time to like really consider this part. They're like, let's just get results. So these might be a little too conservative in that actually trying to put their, what's it called? Actually finding results. So one thing I will say is that besides just using these corrections, you can do them and just use that to kind of like reconfirm, say, oh, is this a huge effect or not? And then if it doesn't, maybe consider, okay, like maybe you need to look this a little bit more carefully, or, kind of be aware of these things. But these are one solutions to it. Essentially, the Bonferroni correction basically adjusts your alpha value. So you can see here, essentially, it's like we divide our alpha value by the number of comparisons. So if we make 5 different comparisons, for 5 different parts, we just divide the alpha value by that number. However, this is like really conservative and it's unlikely to pass any test. Like almost no tests will pass this if you make multiple comparisons. Basically, the only ones that will pass is like if there really, really is an effect, which can be useful, but also can be really like worthless in the sense of being like, well, I wanted to see if there was effect and now I can't tell because essentially I'm being more conservative. Essentially, things have to be really, 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 really weird until you say there's an effect. So the Holm-Berfoni kind of does this a little bit better, where essentially it adjusts the alpha value by dividing it over, but there's multiple steps. I'm gonna go through this relatively quickly, so I'm not gonna like harp too much on it because it is here in the Wikipedia, but I'll kind of like show you a little bit what the steps are. And also you probably won't use this in industry, but I think it's an important thing to do. So essentially what you're gonna do is you make M comparisons. So let's say you're comparing 5 different times, and then you calculate the p-value for each comparison, right? You sort the p-values from smallest to largest, right? So basically most significant to least significant, going from 1 to M. So this is like very mathematical, right? Then what you do, you find the smallest k where this is true. We're basically saying the p-value is greater than the alpha value, so let's say 0.5, divided by essentially that comparison. So as you go through k, essentially your alpha value gets smaller and smaller and smaller, okay? And essentially what you're doing is taking the most significant and being the most stringent on that most significant, and then as you go further and further, being like less stringent on that critical. So essentially this Berfoni correction would be like the strictest part, but you get less strict as you go through, okay? And then what you do, you only reject hypotheses associated smaller than the K index. So basically some of your hypotheses will pass and some of them won't. What is kind of nice is that if you have the extreme values, is that if K basically is 1, you don't end up rejecting anything. Basically the first p-value is larger than your most stringent alpha, right? So if you imagine like K is like 1 here, okay? Well then M, you know, it's the number of comparisons divided, basically it's the largest one here, versus like K is like larger, right? Is that this will make a relatively decent sized alpha. If K doesn't exist at all, so there is no K that doesn't exist, all p-values are smaller, then we reject everything. So basically you can do this relatively quickly. For the most part, you could write this in code and stuff like that and do this. It helps kind of balance the fact that it's conservative, like being conservative, but also not too, like being careful about multiple comparisons and stuff like this. So I think, let's see if I put any extra stuff. Yeah, so, oh, this is for the statistical nerds, you know, looking into this, it's uniformly more powerful, which I won't go into the full details of this. Again, this is why it's more focused on academia and stuff like this and maybe things. And I say relatively simple. I know that probably me explaining it doesn't sound very simple, but you can implement this and not have to worry about like what alpha should I actually use. Also, like I kind of put in here, closed testing procedure. There's a whole reason for this stuff too. So if you're interested in this and kind of looking more, there's a couple Wikipedia articles that do a pretty good job of explaining this part. And honestly, it might take a while for you to kind of just like read it through and understand it, but it's an option that could be happen. That can happen. And so, yep, to code, to do. Good old to do. All right. So anyway, in reality, you probably don't have to do this. Like it's a nice thing to do. In reality, you just have to be a little careful about when you're doing comparisons and just be aware. It's like, okay, if I'm doing multiple comparisons, I might accidentally reject something when I really shouldn't have. So I think that's kind of more powerful than any one method to do. Okay, so cool. All right, and I think we're about done, but going off of A/B testing or t-test, Welch's test, statistical power, are there any like lingering questions? Okay. Cool. So next time we'll talk about ANOVA. We'll go into that. We'll talk about like multiple, basically that's part of the multiple comparisons. And we'll probably talk a little bit about how like mathematically that's similar to a t-test or really similar to like a linear regression. Okay, cool. So I'll stop recording here.